Okay, so we have a question here. It says, given a consumer has the following Cobb-Douglas utility function, u x y equals x to the power half, y to the power half, and a budget line of 120 equals 2x plus 3y. Required, state and define the equi-marginal principle. So the equi-marginal principle is telling us when the additional satisfaction per one quadrant of one good is equal to the additional satisfaction per one quadrant of another good, then the consumer maximizes the utility. So let me write it down. When the additional satisfaction per one quadrant of good x equals the additional satisfaction per one quadrant of good y, then the consumer maximizes utility. Okay, basically you get the most satisfaction when the additional satisfaction per one quadrant is equal for all goods. So the additional satisfaction per one quadrant for good x can be written like this: MUX. Think of it as the value for your money. Okay, each time you spend money, you want to spend it so that you get the most satisfaction. That's what the marginal utility divided by the price is. Okay, it's just telling you the value of the money that you're spending. So this is the condition for the equimarginal principle. All right. So we've defined it when the additional satisfaction per one quadrant for all goods is equal, then the consumer maximizes satisfaction, and we've written it down here. So part 2 is saying, using the condition in 1 above, find the optimal bundles of x and y that optimizes utility for the consumer. So basically, we'll find the combination of good x and good y that will make the consumer the most satisfied. So first things first, we have our budget constraint equation here. 120, let me write it down here, 120 equals 2x plus 3y. Okay, this 120, this is your income. This 2 is the price of good x, px. Then x here, this represents the quantity of good x. This 3 is the price of good y. And this y represents the quantity of good y. That's our budget constraint equation. Then our utility function. So these fractions, I'll convert them into decimals to make life easy. So half in a decimal is 0.5, y to the power 0.5. So we need to get our marginal utility for good x. So it means we're going to partially derive our utility function with respect to x, meaning we're only deriving the x variable. Okay, so when we derive, we multiply the exponent multiplied by the coefficient. 0.5 times 1, that is 0.5. And you subtract a 1 from the exponent. So 0.5 minus 1, that is negative 0.5. Y to the power 0.5. Okay, so this is the marginal utility for good x. Then the marginal utility for good y, we're going to derive the utility function with respect to y. So only y is the variable that we'll be focusing on. So in this case, you get the exponent for y, 0.5 times the coefficient, you get 0.5 here. The x variable, you leave it with its power, x to the power 0.5, y to the power. You subtract a 1 from the y exponent, 0.5 minus 1, you get negative 0.5. Okay, so now we can substitute here because we need to get our optimal bundle, the bundle that will give us the most satisfaction. So remember, a bundle is just a combination of one good and another good. So mu x here we substitute it with our marginal utility for x, which is 0.5, excuse me, to the power 0.5 x to the power negative 0.5 y to the power 0.5 divided by the price of good x is 2 kwacha. We got from our budget constraint equation. Equals marginal utility of good y 0.5 x to the power negative 0.5, oh, x to the power 0.5 y to the power negative 0.5 over 3, the price of good y, which is 3 there. Okay, so basically here we have to make one variable the subject of the formula. Okay, so there will be a lot of operations we need to do. So you can either start by dividing 0.5 by 2 and 0.5 by 3. You can get your values. Okay, or you can do it like this. You can cross multiply. Okay, so 3 times 0.5 x to the power negative 0.5 y to the power 0.5. So that would give us 1.5 x to the power negative 0.5 y to the power 0.5 equals 2 times 0.5 x to the power 0.51 y to the power negative 0.5. That will give us 1 x to the power 0.5 y to the power negative 0.5. Okay, so here, since we've got negative powers, so x to the power negative 0.5, we bring it down, so it becomes 1.5 y to the power 0.5 over x to the power 0.5 equals x to the power 0.5 over y to the power 0.5. Okay, this negative y to the negative to the power negative 0.5 comes on the bottom. This is the law of indices being applied here. Okay, even this x to the power negative 0.5 comes to the bottom. Then you have to cross multiply again, okay, because here the thing is this: we want to make one of these variables the subject of the formula. All right, so multiply 1.5 y to the power 0.5 times y to the power 0.5, we get 1.5. Now, if you remember with indices, when you're multiplying the same base, you add the indices. So when you multiply this y to the power 0.5 times y to the power 0.5, Same bases, so you add the powers. So 0.5 plus 0.5, that gives you 1. So you get 1.5 to the power y. Similar with x. X to the power 0.5 times x to the power 0.5. Same bases, so you add the exponents. So this 0.5, you add it with this 0.5, and you get x to the power 1. Okay, so x equals 1.5 y. Okay, so that was the whole purpose here. We just wanted to get either x as the subject of the formula or y as the subject of the formula. So this, you are going to substitute it into the budget constraint equation so that we can find how much of good X this person needs to buy and how much of good Y they need to buy. So we're going to substitute X for 1.5 Y. So if you remember our budget constraint equation, it is 120 equals 2x. Now this x we substitute it with 1.5y. So 2 times 1.5y plus 3y. So 2 times 1.5y, that is 3y plus 3y. 3y plus 3y, that is 6y. 120. So we have to get our value for y, divide both sides by 6. 120 divided by 6, that is 20. So this person needs, with their budget, to make them happy, for them to get the most satisfaction, they need to get 20 units of y. Now we need to find how many units of x do they need to get. So remember, x equals 1.5y. So we're going to substitute. Hello. Hello. I'm recording. I love you too. Yes. So x equals 1.5y. So y equals 20. So we substitute y with 20. So 1.5 times 20, 30. All right. So this person will get the most satisfaction when they buy 20 units of y and 30 units of x. That's when they'll get the most satisfaction. Then part B, use the tangent condition on how a consumer is optimizing utility. So the tangent condition, colleagues, this is where the slope of the indifference curve, which is the marginal rate of substitution, okay, MUX over MUY. This is the slope of the indifference curve. Remember, indifference curve shows combination of x and y with the same satisfaction. Now, when the slope of the indifference curve equals the slope of the budget constraint line, the slope of the budget constraint line is this, then the consumer has maximized satisfaction. Okay, and so we can also use this condition to get the optimal quantity for satisfaction for this person. Okay, if you remember, marginal utility of x was 0.5 x to the power negative 0.5 y is to the power 0.5 divided by the marginal utility for y was 0.5 x to the power 0.5 y to the power negative 0.5 equals the price of good x was 2 kwacha, the price of good y is 3 kwacha. Okay, so using this, these cancel each other out. This is x to the power negative 0.5 over x to the power 0.5. Remember from indices, when you're dividing same bases, you subtract the indices. So x to the power negative 0.5 divided by x to the power 0.5. So we subtract negative 0.5 minus 0.5. And we're going to get a negative 1. Then for y, we subtract this 0.5 minus negative 0.5, you get a 1. Okay, equals 2 over 3. And then this is x to the power negative 1, so it goes at the bottom, so it goes as y over x equals 2 over 3. Okay, and here we can try to find the value of any. So here let's find the value of x. Let's make x the subject of the formula. So x times 2, that is 2x. Cross multiply, then 3 times y, that is 3y. So to find the value of x, to make x the subject of the formula, 3 divided by 2, that is 1.5. So x equals 1.5y. And if you remember earlier in our question, that's the one we found here. X equals 1.5y. And that will help us get our optimal bundle, because when you substitute this back into the budget constraint equation, you get these bundles: 20 units of y, 30 units of x.